Hey everyone, and welcome to the second half of part 5 of this series where we code a fitness tracker with Python. Let's continue where we left off. So first of all, I've added some extra information to the document that we have been using in the previous episode. So make sure to check it out again. And the most important thing that is updated over here is a new Python file that we will be using. So that is the frequency abstraction.py file. So make sure to add this file just like the previous files also to your project directory, so your workspace in Visual Studio Code. So make sure it is in the features folder, and then here we have the frequency abstraction.py. So this is the new one that we will be using in this episode. So let's continue where we left off. So the last thing we added to the script was the sum of squares attribute to add some additional features. Let's now continue with temporal abstraction. So let's first quickly cover what we mean by temporal abstraction. What we are basically going to do, we are going to use a rolling window walking over our data, and for a certain window size, we are going to compute the average, so the mean, and the standard deviation. So here's a visual image of a rolling average in Pandas, and you can find out more about this source over here by following this link. But basically, this gives a good understanding of what we are going to accomplish. So here we have the raw signal in this case. So this is from another dataset. And then here in the orange line over here, you can see a rolling average, basically meaning that depending on the window size, we're going to look back, for example, let's say 5 steps, and then we're going to compute the mean, the average of those 5 previous steps. And then we're going to input that as a new feature. And we walk over the whole data frame, over the whole data set, and for each of the records in there we compute this value. And we can do this with all kinds of statistical properties like min, max, median, mode, mean, etc. And this can help us to basically summarize the data for a given window size, and by that adding extra information, providing extra information for our model. So we will be using the mean and the standard deviation. Those are the values that we will be computing, and luckily Pandas has a very nice feature, a very nice method in order to do this very quickly. So let's see how that works. So we'll start off as usual by defining a new data frame and creating a copy of the last data frame that we've used. So we continue from the df squared, so make sure that all the previous code that we've created in the previous episode is active again in the interactive environment over here. So make sure to run everything, and then you can check that we have df squared, and it should look like this. So 15 columns and 9009 rows. And then let's continue by creating a copy. Next, we will be using the numerical abstraction class that we have imported. So let's define a new variable over here called numAbs and set it to numerical abstraction. And basically by doing this, we initiate a new class instance like we've done previously already. But now let's have a look at the numerical abstraction class over here and see what is in here. So we have 2 functions. We have an aggregate value function and we have an abstract numerical function. And basically, this is a convenient function to extract the different statistical properties for a given window size, like I've just explained. So as we can see, as input, we take a data frame, a data table. Then we select the columns for which we want to extract the features. Then we specify a window size. So that determines how far do we want to look back into our data frame. And then also the aggregation function, which is one of the values that you see over here. So if mean, max, min, median, standard deviation. So that is how this temporal abstraction.py file works with the class numerical abstraction in it. So by initiating the class like this, we can now use this variable over here and call the different functions in order to process the data set and add all the features. And now, just like the previous examples, we're going to loop over all the columns for which we want to add the temporal features. And we have the predictor columns, which contains the first 6 columns of the data frame. But now we're also going to add the columns that we've just created in this section over here, so the sum of squares. So that will be 2 additional columns. So that is arc R and gyroscope R. So if we add that to the predictor columns, we can see that we get a new list. And now all we have to do is store that into the variable itself in order to store it in place. So now we can see we have added 2 extra columns to the predictor columns. Now the next step is to determine the window size. And as I've just explained, the window size basically captures how many values we want to look back for each of those values. So if we look at the data frame over here, if, for example, we're at this value over here, if we use a window size of 4, for example, it will look at itself, then this value, and this value, and then it will compute the mean or the standard deviation based on these 4 values. And that is the value that will be added on this row and then in a new column all the way on the right. So that is how that works. And now finding the optimal window size is, as usual, a process of trial and error, and also something that we should reflect on and evaluate later after we've created our initial models. Then we can also play around with the window size and see how it affects the performance of the overall model. We also have to keep in mind by using a window size of, for example, 5, this means that we can't use the first 4 values of the data frame. And later we will be splitting the data based on the individual sets, just like we did in previous examples. So we have to remember that by setting a very large window size, we also throw away a lot of data that we can't use because it will result in missing values. And to keep things simple for now, we are going to start off with a window size of 1 second. So in order to compute that, remember that we have a step size of 200 milliseconds. So in order to determine the window size for 1 second, we take 1000 milliseconds and we divide it by 200, so our step size, which will result in 5. Meaning that in order to get a window size of 1 second, we need 5 steps. So we need 5 instances. So to make this neat, let's just make it an int. And then we have a window size of 5. Now, the next step is to loop over all the predictor columns and then compute the mean and the standard deviation. So as usual, we're going to create a for loop where we say for call in predictor columns. So this will create the loop. We will say df temporal because the function will add to the data frame. So we're going to say numerical abstraction, and then we're going to call abstract numerical. And then remember, we can check out what function or what parameters the function takes over here. So we have data table, column, window size, aggregation function. So we'll start off with the data table, which is the df temporal itself. Then we need the columns. So that is going to be col, but it has to be in a list format. Then the window size, and then first we're going to compute the mean. And then second, we're going to Command C and Command V to copy paste this line and then just replace this with standard deviation. This will loop over all the predictor columns, the columns over here, and it will add to the df temporal data frame the numerical abstractions with a window size of 5, and it will compute the mean and the standard deviation. So let's run this code and look at the results. So this takes a while to process because it is looping over all the columns and doing the computations. So let's see how long it takes. All right, it's finished. And now let's have a look at our df temporal. So we can see that we have a lot of additional columns in our data frame now, because for all of the predictor columns, we create 2 additional columns, mean and standard deviation. So let's look over here and see what we have. And here we can see that for every variable over here, we have a temporal mean with a window size of 5, temporal standard deviation with a window size of 5, and that for all of the columns. And we can also see that the first 4 values are missing because the window size is 5. We use the value itself and the 4 previous for a total of 5 records, and it can't compute these because it doesn't have values earlier than that. Now, this is starting to look good, but remember, just like in previous examples where we looped over all the data, that we are basically introducing noise or errors into the data set, because by looking back 5 steps and looping over the whole data frame, whenever you switch from one set, so for example a squat, to the next set in the data set, which could be, for example, a bench press, the first value, so the first row of that new set, so for example the bench press, will look 4 steps back into the data frame and then use those values that are from a squat to compute the mean values and standard deviation. So we are introducing data that is originally from a squat into a bench press set. And that is, of course, something we don't want, because it will probably result in a worse performance of our model, because we are introducing values that are just not true, that are not relevant for the set. So in order to fix that, we are going to split this loop up into a subset where we basically make a subset based on the set and then compute the values for each of the individual sets. So let's do that right now. And we will start off by creating a list that we will be appending subsets to. So we'll start off with an empty list, and then we're going to loop over the unique sets in the data frame. So for S in df temporal, and then we'll take the set column and then call unique. Then let's select a subset, the unique sets, and set this to S. So we'll loop over the unique sets, then create a subset based on this selection. And in order to avoid some warnings, we create a copy. And now with the subset created, we're basically going to copy and paste what we've done previously. But now make sure to swap this around with the subset. And then once that's done, we have to add it to the df temporal list. And we say .append, and then we just append the subset. And now once the loop is completed, we call pd.concat, and then we put in our df temporal list to bring back everything together. So the df temporal list will contain a list of separate subset data frames, and then by calling the pd.concat method, we bring everything back together into one data frame again. Let's make sure that the list is stored, and now let's run this piece of code to loop over the whole data frame. All right, and we're finished. And now let's have a look at the concatenation, see if that makes sense. Okay, looking good. So let's store this into the same, not in the list, but in the original data frame. So we're going to override it, and then let's check it out. Okay, awesome. So what we've just done is we've looped over the unique sets, and for each set we've added the mean and the standard deviation. And by looking at the data frame right now, we don't see much of a difference compared to the previous results. It's still same amount of rows, same amount of columns, and the first contain missing values. In this data frame over here, there are actually a lot more missing values. Basically, for each set, the first 4 rows will be missing, and we can check that out by calling info on the data frame and then have a look at all the values that we've just created over here, and we can see that there are quite a few missing values in total. But by doing this, we have basically countered the data spill, so to say, of the different sets into the next set. So we lose some of the data, but it's still the best option to go with in this case. All right, and now finally, let's have a look at the result. So we can just take the subset variable, and that will contain the last set of the loop. So this is just at random, but this is set 71. And let's just take an example of the y acceleration, and then we're going to copy and paste this and make sure it's the y, and then this is the mean, and then take the standard deviation as well. So let's just check it out. Yes, okay. Then create a plot. All right. So here we can have a look at what we've accomplished. So we have the y acceleration in blue, and then we can see the mean is in red orange over here, and we can see it's basically a very smoothened out version of the original value, and that is because it's taking the mean over a period of time, so it smooths everything out. And then on top here we can see the standard deviation as well. Let's copy this line of code and do the same for the gyroscope. So select this and hit Command D 2 times, and then type in gyroscope. Do that as well, and here we can see the same graph, but now for the gyroscope data. So also a smoothened version of the original value and the standard deviation. All right, and with the temporal abstraction out of the way, that brings us to the frequency features. And these require some of an introduction. We will be using a technique called discrete Fourier transformation in this case. And basically, to give you an idea of what a Fourier transformation is, I have some information provided here. So first of all, here is a description from the book Machine Learning for the Quantified Self. So the idea of a Fourier transformation is that any sequence of measurements that we perform can be represented by a combination of sinusoid functions with different frequencies. This is an illustration that I found online, so it's from this source over here. I think this really illustrates well how we can decompose a signal into its different frequencies. So that is basically the goal of applying the discrete Fourier transformation. We're going to look at the individual measurements and then, using a lot of complicated math that we won't get into in this video, decompose the original signal into the different frequencies. So we will be extracting the different frequency components, and here's another description of why this is helpful to machine learning. So more efficient analysis of the data, because it provides a way to better understand and model complex data sets, as the frequency components produced by the DFT can provide insights into patterns and trends that would not otherwise be visible. Some of the features that we will be extracting are the amplitude for each of the relevant frequency that are part of the time window, the max frequency, weighted frequency, which is the average, and the power spectral entropy. So I have to say here and state that these frequencies are part of the machine learning for the quantified self case studies that are explained in the book and also on GitHub. And the code that we will be using to compute all these values is in the frequency abstraction.py file that we've added to the workspace at the beginning of this video. So here you can see how everything is calculated. So here we have the max frequency, the weighted, the power spectral entropy, and here the amplitudes for each of the frequencies available in the window. But the math behind these calculations is very complex, and I have to admit that this is also outside of my area of expertise. So we're not going to dive into this. So here you have a Wikipedia page where you can find some information about the math behind these calculations. So I won't and also can't explain how everything works behind the scenes that we are about to do, but that is also not my goal. I just want to show you what a Fourier transformation looks like. So input data, output data, and then later show you how the new features that we've generated affect our model. So please keep that in mind. This is also outside of my area of expertise. I'm just following the principles from the book and the GitHub repository of the machine learning for the quantified self. All right, so let's get started. So we're going to create a new frequency data frame and create a copy of the previous data frame. And we're also going to reset the index because the functions that we are about to use expect a discrete as an input. And now we have a time series index. So let's just reset the index and then check what it looks like. So we have the same data frame, a copy, but now we have a discrete index from 0 all the way to the last value. And now, just like with the numerical abstraction, we're going to import the class and initiate a new instance. So we first have to add the import. So we're going to do from, and this is the frequency abstraction. We're going to import the Fourier transformation class. So let's run this and then come back to our code, and we'll create a new variable called freq apps and then set that equal to the Fourier transformation class, and let's initiate it. And let's have a look at what we are actually doing right now. So we are creating a new instance of this class, and in here we have two functions. So we have find FFT transformation, and then we have the abstract frequency function. So these are the functions that we will be using, and we also have some documentation over here about what kind of parameters we need as an input. We are going to use the abstract frequency, which takes as input the data table, the columns, the window size, and a sampling rate. So it's kind of similar to what we saw with the temporal abstraction and then the numerical abstraction. So we have a data table, column, window size, and then here we have an aggregation function, and with the frequency, abstract frequency, we need a sampling rate. So let's see how that works. So let's start off by defining the sampling rate and the window size, and if we come back to the documentation over here, we can see that the sampling rate expresses the number of samples per second, and that is 5 in our case, but let's define it properly. This will result in 5. And then for the window size, this time we are going to set the window size to the average length of a repetition. So that was about 2.8 seconds. So we will set that to 2800 milliseconds, then divide it by 200, which will give us a window size of 14. Meaning that we are going to compute all the frequency features with a window size of 14. Okay, so let's see how that works. And let's just first apply the Fourier transformation to one column as usual to get an understanding of what this will result in. So we call our frequency apps variable and then do a dot and then call abstract frequency, and then let's check, what do we need? We need data table, column, window size, sampling rate. All right, so we just pass in the data frame, start with the Y acceleration, and then we're going to do, let's check what's the first one first, window size. So we do window size and then sampling rate. Let's have a look. So this takes some time to compute and we get an error. And that is because just like with the numerical abstraction, the column is expected to be in a list because we can also input multiple columns. So let's run that one more time. It should work right now. So this takes some time. All right, and once it's finished, we can have a look at our new data frame. Good, and we can see that we have some additional columns. So if we compare it to our previous data frame, the temporal one, we had 29 columns and now we have 41 columns. So if we have a look at the columns, we can see that starting from here, these are all the columns that were added. So max frequency, weighted, and the power spectral entropy, and then all the different amplitudes. So this is just for one variable. So you can imagine how if we are going to loop over the data frame, over all of the predictor columns, we are going to add quite a few columns to the data frame. So now let's have a quick look at what we've actually did. So let's just first create a subset for set 15, just random, and then plot this over here. So here we can see the Y acceleration for set 15. And now let's have a look at some of the values that we've added. And here you can see what that looks like. So I've plotted a couple, max, weighted, power spectral entropy, and 2 random amplitudes. So all the complicated math that is happening over here results into the values that you see over here. So that was for one column. Now let's apply the same trick that we did over here by looping over the data frame and all the columns, and also splitting by set. And here I'm going a bit faster because this is basically the same as we've already did. So we create a empty list that we are going to store the subsets in. Then we're going to loop over the unique sets within the data frame. Then I'm also going to add a print statement here because this can take a while, so you get an idea of where it's at. And then we create the subset based on the S that we're looping over. And then we're going to extract all the frequency features. And it's nice that we can add a list of columns in here, so we don't have to actually loop over everything, but we can just do it like this. And I think, yeah, we could have also, we could have actually done that here as well, I noticed. So the loop over here was probably not necessary, but hey, if it works, let's just not touch it. But let's just make this a bit more efficient by just adding the predictor columns in here instead of looping over everything. And let's see what we're doing right now. So here you can see that it's applying the Fourier transformation set by set. And here you can see that it takes a while. That's why it's nice to have the print statements. And depending on the machine that you're running this on, this could even take longer or go faster. So let's wait for this to complete. All right, and we're done. So now let's do the same trick again, where we do the PD concat and then put in the frequency list, and then let's see what that results in. So we have a total of 107 columns, and we can see that we have now more missing values in the frequency domain because we use a larger window size, and we will deal with that in a bit. But for now, let's just store this in the data frame and overwrite it like this. So then we have our original data frame again, now with all the additional values, and we're going to add one more statement over here, and that is the set index. We're basically going to take the index and set it back, or the original index, and set it as index again, and drop the discrete index that we're seeing over here, which should also be reset, as you can see, because of the loop that we were using. So now let's just run this, and then let's have a look. And now we have our original index. So that was just an intermediate step in order to get this function to work. And now we're back to where we were. And now before we continue, I have to correct a small error. So I will indicate this in the video so you won't make that error. But just to keep that in mind, I'm going to put the gyroscope R here and not the Y. So we were missing some values because we were adding the gyroscope Y another time that was already in the predictor columns. So in order to correct this in my situation, I have to basically run everything over here again, but now with the correct values, and then do that also one more time for all the frequency features. All right, and after running everything again, we should now have this final data frame with 119 columns. So if you've been following along and paying attention to the mistake that I've made and corrected it earlier on, this should be where you are at. Okay, so the next step is dealing with overlapping windows. And now you can imagine, since we've added all these extra columns, which are all based on a rolling window, that the values in all of the columns between the different rows are highly correlated. And this is typically something we want to avoid when we are building models, because this could cause overfitting. In order to tackle that, we're going to allow for a certain percentage of overlap and remove the rest of the data. So let's see what that looks like. But to start off, we are going to drop all of the missing values that are currently present in the data frame. And in order to do that, we're going to take the latest data frame, so they have freak, and then call drop. And let's see, if we run the original data frame, we can see that there are 909 rows in here. But if we drop all the missing values, we can see that we got rid of quite a few rows over here. So about 1300 in total. And that is the result of the window size of 14 steps that we've applied during the calculation of the frequency features. We get rid of those and then store it into the data frame. And now we can see we have a new data frame with less rows in total, but no missing values. Now, and in order to deal with the overlapping windows, we're going to get rid of some part of the data. And when you look in the literature, typically an allowance of 50% is recommended, meaning that in our case, we will get rid of 50% of the data by skipping every other row. And this will result in a lot of data loss, but it has been shown to pay off in the long run by making your models less prone to overfitting. And in our case, we still have enough data, so we will use the 50% window or overlap in this case. But when you have very small data sets, you could also change this number to allow for 80 or 90% overlap, meaning that you will get rid of less rows overall. But in order to do this, we can use the ilog method of the pandas library. And typically how you use this is you first specifies the rows that you want. So for example, I want all rows, all columns. If I do it like this, I get the original data frame. But now what we can do, we can also just do it like this and then specify just all the columns and then say, I want everything up until the second row. So that is how you normally use ilog, but there is another way you can use ilog, and that is if you add another semicolon over here, another column, then you can specify that you want every other row or every second row, basically. So if I run this, we can see that we now have a resulting data frame that is half the size of the original data frame. And if we look over here, we start at 0, then we go to 200 and then to 400. If we compare that to parsed data frame, we see that we start at 0 and then we go to 400. So we skip the 200 one, meaning that it will skip every other row and then starting from the first initial row of the data frame. And in doing so by removing every other row, we basically reduce the correlation between the records, the adjacent records that are in the data frame. And yeah, as I've explained, this reduces potential overfitting of our model and has proved to be a solid method for dealing with highly correlated values as the result of multiple aggregated features using a window. So let's store that into our original data frame. Make sure that it is stored and saved. Check it out. Okay, so we now have a much smaller data frame, still 119 columns, and now it's time for clustering. And for this, we will be using the k-means clustering library from the sklearn package. So first we have to import that. So we're going to import from sklearn cluster, import k-means, not k-means. Hey, we don't want k-means plus, we want k-means. This is the one. Yes. All right. So import that, make sure it loads correctly, and then we can continue with adding clusters. So first, very briefly, what is clustering? And k-means clustering in this case. So it's an unsupervised machine learning algorithms that we can use to group data into clusters based on their similarity. And how the k-means algorithm works is we start off by defining k, that is the total amount of clusters that we want to use. And then it basically calculates the distance between each of the data points and the centroids that it has defined. So based on how close they are to that centroid. And so this is a popular feature engineering technique. And as I've said, it's an unsupervised learning algorithm. So we can basically provide the data and the amount of clusters that we want to use to the algorithm. And then it will basically group all of our individual rows to a specific cluster. So we can basically group based on a unsupervised learning algorithm. And this is typically done for segmenting customers, purchase behavior, anomaly detection, image compressions. So a very useful technique, and we will be applying it to our sensor data set in order to see what kind of groups it can come up with. And again, just like with the principal component analysis, we can use the elbow method here again. But now using different values, namely the inertia, which is the sum of squared distances of samples to their closest cluster center. And we will be computing that for each k, so for each number of clusters. And we will basically loop over various numbers of k and then create a plot like this, which is taken from this resource, this webpage over here. So here you get a better understanding of how this works and also see some more code examples. But this is basically what we will be doing. And we will use this to determine the optimal amount of k for our data set. Okay, so let's come back to our code and we'll start off by defining our cluster columns. But because we definitely don't want to cluster on everything that is in there, we are going to limit it only to the acceleration data. So that will be the x, the x, y, and z of the accelerometer data. That is what we will be using to cluster on. And then we're also going to set a range for the amount of k, the amount of clusters that we want to test. And for this, we'll define k values, and we're going to state that in a range from 2 up until 10. And now we are also going to store the inertias in a list, which we'll first define as empty. Make sure to run everything. And now let's loop over the data frame and create the clusters. But before we start, let's create a quick copy of the data frame. So we create df cluster will be a copy of df. And then let's just copy it. So now we have a new data frame, and then let's go ahead and say for k in k values, we're going to create a subset based on the cluster, not the cluster columns, first the df cluster, and then creating a subset by inserting the cluster columns. So this will be a subset based on only the columns that we want to cluster on. And now we're going to define our k-means model, and we're going to set that equal to k-means, and then k will be equal to k, and then the init will be equal to 20 in this case, and the random state will set to 0. Oh, sorry, it's n init in here, not the init, but the n init. And now let's continue by specifying the cluster labels, and we're going to do a few steps in one here. We're going to call the k-means, and this is a scikit-learn model. And typically if you've worked with the scikit-learn library, you first do a fit and then you do a predict. But most scikit-learn models also have a fit predict method that you can use to instantly train the model and also make predictions. And that is what we're going to use in this case. So we're going to use this model and then input our subset as the input. So what this will do, we have initiated a k-means model over here with k set equal to the k that we're looping over. The next step, what it will do, it will take that model and call the fit predict, then input the subset and create the cluster label. And what it will do by calling the fit predict, it will, for each of the rows that is in the subset, it will assign the row to a cluster. And on the first iteration of this loop, k will be 2. A row can either be assigned to cluster 1 or cluster 2. So that will literally be value 1 or value 2. Then on the second iteration, k will be 3. And then naturally, each row will be assigned to one of 3 clusters, 1, 2, or 3. And it will do that all the way until k is 10. We will store the cluster labels over here, but the next thing that we have to do is we have to store the inertias, because we want to use the inertias to plot them on a graph and then use the elbow technique to determine the optimal amount of k. So this is just a preparation step in order to determine what we are going to use as k. So the final step over here is to call the inertias list, call append, and then we're going to call k-means, and then we can call dot inertia underscore. So if we take a look at the documentation from the scikit-learn library and look at the k-means library, here we can see all the parameters that we can adjust to tweak the performance of the model, but we can also see the attributes. And these are the attributes that we can call upon after fitting the model, so after training. And here you can see we can call inertia underscore, which translates to the sum of squared distances of samples to their closest cluster center. So that is how this works and why we can call k-means inertia underscore. So to summarize, loop over all the values, create a subset, train the model, export the inertias. Let's run this, see if everything works. Oh, and we get an error over here because as you can see, it's n clusters and not k. So I have k is k here, but we need n clusters equals k in this case. And now if we run this, it will succeed. And then we can plot the inertias. Let's make sure I run this twice. The values over here, so 2 all the way to 10. And now we can use this list to create a plot and visually inspect whether we can determine an elbow. And in order to plot the graph, I'm just going to copy and paste this code over here. And we get this result. And this is looking like a textbook example, as we can clearly spot the elbow over here. So you could discuss like, should the optimal amount be 4 or 5? But I would argue that 5 would be the optimal amount of clusters in this case. As you can clearly see that this is like the elbow joint, and afterwards the decrease in sum of squared distance diminishes. So what we will now do is we will basically this piece of code over here, but now we're going to, instead of looping over k, we're just going to set n clusters, so k equal to 5, and then define our model as that, so with those parameters. Then we're going to create the subset again, which is, as you can see, the same as before. So our df cluster is still the data frame that was just a copy of the frequency data frame. And now we are going to call the cluster labels, and we can even get rid of that. What we can do is we can say df cluster and then specify a new column called cluster, and then call fit predict on the subset with, make sure to run this line first, that is set to 5, run all of this, and then let's see what the result is. So now if I have a look at this data frame, we can see that we have one additional column, 120 in total. And if we go all the way to the back, I can see that we have a cluster column over here, and we can only see, oh no, there's also a 4 over here. The cluster starts at 0. So previously I indicated that it started at 1, but I see now that it starts at 0. So it's 0 indexed. We have a total of 5 clusters, so 0 all the way to 4, and each record is assigned to a specific cluster. So now let's have a look at what it looks like visually, to see if the clusters make sense. And in order to do this, I'm going to copy and paste another block of code in here that you can follow along yourself. But just to save some time, I'm going to run this. And this is a very cool plot in my opinion. So what we are doing right here is we are using the projection 3D from the matplotlib library. And then we're looping over the data frame and then splitting by cluster. So we're calling the unique method again to loop over all the individual unique clusters, then create a subset. And then this is the interesting part. We're creating a scatter, but instead of what you typically do is inserting 2 values. So typically it's an X and a Y, and you get a 2-dimensional scatter. Now we can input 3 variables, X, Y, and Z. And by stating that this is projection is 3D, we get a 3D plot with the 3 different axes. So this is very cool. And here on the legend in the top right corner, you can see which color corresponds to which cluster. So this looks very cool, and we can clearly tell that the clusters are grouped together, meaning that there are green clusters over here, yellow, blue, etc. So you can also see some noise over here. So for example, there are also some points over here that are allocated to the blue cluster, which is cluster 0. But you could argue, like, do they really belong to this cluster? But of course, this model is never perfect, but from just this visual inspection, it looks really good. But now to really put it to the test, we should compare this plot to the same plot, but then splitting not by cluster, but by label, so by exercise. So let's do that right now. And this will be another block of code, which is basically the same, but now instead of looping over the unique clusters and then creating a subset based on cluster, we're going over the unique labels and then subsetting by label. So everything else is the same. And now if we run this, we get another plot. And now the interesting part, what we can do here is we can have a look at the individual exercises and see where they belong within this three-dimensional plot. So we can see that the bench press and the overhead press very close to each other, which is to be expected because the movements look a lot like each other. Then also in green and gray, we have the deadlift and the row, which also look very similar to each other. And those are grouped over here. Then we can clearly see that the squat is very different from all the other exercises, and the rest is all over the place, which is also to be expected because rest is pretty random because the participants were not restricted to certain movements. By looking at the clusters and then at the images over here, we can clearly see that, for example, cluster 3 definitely corresponds to the squat over here. And similarly, we can see that cluster 0 probably captures the bench press and the overhead press data. And here you could also argue the decision to create 5 clusters because we have 6 labels in total and we are using 5 clusters. So you see that it's grouping the overhead press and the bench press, it's grouping them together in the same cluster. And also you don't really see that much of a difference between the deadlift and the row over here, which if I look at the clusters also seem to be grouped together. So this is very interesting, but potentially a lot of valuable information that could benefit our predictive modeling. And that brings us to the final step of this episode, and that is, as always, exporting the data. So we will take our cluster data frame and we are going to pickle this, so by calling toPickle, and then we'll store this in the intermediate files again, so data interim, and then we're going to store this as o3 data features.pickle. Let's run that, have a look at the final data set. So you should have a cluster column over here, 120 columns in total, this amount of rows, and then we can export it. And that brings us to the end of this episode. Now, please like this video and subscribe to the channel. And then I'll see you next week in part 6, where we dive into probably the most exciting part of this whole project, and that is predictive modeling.